Greetings and welcome back. Today we'll be looking at bond rotation. Bond rotation, if we flash back to the last video, bond rotation can happen when a bond is rotating around its axis. So for instance, if a bond is rotating kind of in a circle like that, that can happen with a sigma bond. This right here is a sigma bond with two electrons in between. And a sigma bond is just a single bond, or that is head-on overlap of electrons, where the electrons are shared directly in between those two nuclei. Those can rotate, and you would be none the wiser. And that's what we'll be looking at today, is how that type of rotation ends up with different conformation of the other stuff that's located out here and out here. So let's remember that carbons with 4 single bonds tend to be tetrahedral. So if we drew methane, it might look like this. It would have 109.5 degree angles everywhere in between its hydrogens. So this could be approximately 109.5 degrees, and that's what all of those angles would look like. It's arranged in three-dimensional space so that you have two bonds, this carbon-hydrogen bond and this carbon-hydrogen bond, that are in one plane that would be flat with the board or flat with whatever the monitor is that you're watching this video up on. And you'd have one bond coming out at you and one bond going back into the screen. All right, so what happens if we put two carbons together? Well, if we put two carbons together, we could put a direct bond in between them. And this is where we end up with some options. We could have something that looks kind of like this, which would basically end up looking kind of like a sawhorse, where you would have a flat plane that would encompass this carbon-carbon bond, the two hydrogens sticking up, but then you would have kind of feet down here, one coming out at us, one going away, and on the right side, one coming out at us and one going away. So let's see what that looks like with chemical models that I suggest you purchase or come down to my office and play with. So you can see that in three-dimensional space, all of these hydrogens are relatively well spread out, which is good. So remember that we talked about in the last video that the reason that tetrahedral even exists is that carbon wants to be able to have 4 single bonds that are spread out as far as from each other as they can in three-dimensional space, because of the fact that bonds are populated by electrons. Electrons are all negatively charged, and therefore they all repel each other. All right, so let's look at another possible conformation of this, which I will draw down here. So we could also have a situation with the exact same molecule of ethane, in which the planar bonds, the ones that are straight lines, not the wedges and the dashes, are instead oriented where on the left one it's up, and on the right one it's down. So this isn't quite the sawhorse that we see up here, or in this picture right here, but with a model it would look like this. So once again, it appears that all of these hydrogens, the 3 on the left, the 3 on the right, are all relatively spread out in three-dimensional space. However, these would be called two different conformations of this molecule. Essentially, these arise based on this single bond between the two carbons spinning around. Well, these are just two possible conformations of ethane. Ethane could have the right side of this molecule spin really in any orientation relative to the left. So what's important for us to be able to understand and evaluate is, in three-dimensional space, how would this single bond right in between the two carbons like to rotate? And that informs us for larger molecules, how would this single bond like to rotate? And as we're going to find throughout this class, the reason that these bonds would rotate is so that you could obtain the most stable conformation. So let's look at which of these conformations is most stable and how we can tell. We'll begin with this conformation seen here. This is the one that I described as looking a little bit like a sawhorse, where it almost has feet coming down, laying flat on both the left and the right side. So if you can imagine that your eyeball is right over here, and you are looking right at that carbon on the left, what you will see is you will see that we have 3 hydrogens attached to that carbon. So here's the carbon. I'm going to circle these in yellow. You would have those 3 hydrogens coming off of it right there. Directly behind that, we would have a carbon, and it would also have a hydrogen sticking up, and then kind of down here, over here. So if we take this molecule and rotate it around, this is what you would see from the point of view of your eyeball being on the left side. It would appear to look something like this, where that front carbon is right here, the one in yellow. That front carbon has a front hydrogen down and to the left, down and to the right, and sticking straight up. Directly behind all of those, you would see that there should be another carbon back there. It's right behind, so you can't really see it from this point of view. We have a hydrogen down and to the right there, a hydrogen down and to the left, and there's a hydrogen right up here, right behind. So all of those are arranged where they're sitting basically right on top of each other in three-dimensional space from that point of view. So let's look at the other conformation and the way that you would examine it if you use the perspective of looking from the side. We can see that if we are looking directly at that exact same carbon from the left side, this one, and it has its 3 hydrogens, then in this case, the carbon on the left, which would be at the front of our eyeball, the closest to our eyeball, would have a hydrogen sticking straight down, then 2 up at the top. And that's what we're seeing right here. This front carbon has a hydrogen sticking straight down from that point of view, and 1 up and to the right and 1 up and to the left. Well, the back carbon, the one furthest from our eyeball, would still be kind of overlapping with that front carbon, except that that back one would have 1 sticking straight up, and then the 2 coming down would be off to the sides, and that's what we see here as well. There's that back carbon right in there. It has a hydrogen sticking straight up, and 1 down and to the left, and 1 down and to the right. So we express this with something called a Newman projection. Newman developed a way to be able to look at molecules from this sideways perspective. And he called this a Newman projection. And what we see is that we put that front carbon as a dot, and we indicate where the bonds are coming off of it. So we would have a bond sticking straight up, and then 1 down and to the left and 1 down and to the right. So the way that Newman said to illustrate this would be we have an H straight up and to the right, straight up, then down and to the right, and down and to the left. And then what we would do is illustrate the back carbon as a circle. So the one in blue is illustrated as a circle back there. But notice that everything is kind of right on top of each other. So coming off of that back carbon, we'd have a hydrogen sticking straight up, 1 down and to the right, and 1 down and to the left. All right, so let's do a Newman projection for the one on the bottom. Well, in the one on the bottom, our yellow indicates what's in the front, so we will draw that first. From this perspective, here's our carbon in the middle. We would have a hydrogen sticking straight down, 1 up and to the right, and 1 up and to the left. And then on that back carbon, which we illustrate with a circle, that's the one that we have illustrated in blue in our structure there. We have a hydrogen sticking straight up, and 1 down and to the right, and 1 down and to the left. So as you might be able to tell, when we look at this structure right here and this structure right here, it looks like the H's are spread out plenty in three-dimensional space. However, these bonds are comically long. You don't have a huge space in between those. So in a second I'll give you what this kind of looks like with a space-filling model. But using the Newman projections, which are kind of illustrated in these 4 drawings/pictures right here, what we can see is that in three-dimensional space from the side, these 2 hydrogens, and these 2 hydrogens are actually very close to each other, whereas in this bottom one, they're quite spread out. So we call this top one, for reasons that I probably don't have to explain, an eclipsed conformation, because all of those bonds are eclipsing each other. The bottom one would be called a staggered conformation, because they are much more spread out in three-dimensional space. So let me show you a little slightly different view, add in kind of shorter bonds, so models with shorter bonds so you can see. So with this type of bond, you can tell with these models that these hydrogens are actually close to each other in three-dimensional space, and they don't like that because this area is composed of electrons, and electrons don't like to be close to each other. So in the staggered conformation, they're much further apart, and therefore they're spread, and this is more stable, and so this is how you're more likely to see any single bond is staggered instead of eclipsed. While this is certainly easiest to do with models sitting in front of you that you can rotate around in your hands, it's also something that I'm going to have to ask you to do in your head. But until then, I created a short video for you to be able to see how these molecules rotate around so that we can consider not just the eclipsed and the staggered conformation, but the energy in between. So here is my video within a video. And once again, you can see that this is in that kind of sawhorse conformation that we saw to be staggered, where if you're looking at it from the left side, and I'm going to actually take the right side and point it out towards you, but if you look at it from any of these point of views, if this is the front carbon, you have a hydrogen sticking straight up, and on the back carbon you'd have hydrogen sticking straight up. So these guys would be eclipsing each other. So let's see how we turn that into a Newman projection. All right, so that first Newman projection is, of course, going to be eclipsed. We see that the carbon in the front, which we illustrate with that little dot, has a hydrogen sticking straight up, has a hydrogen down and to the right, and a hydrogen down and to the left. The carbon in the back, which we'll again draw in blue, is going to have a hydrogen sticking straight up directly behind that one, a hydrogen down and to the right directly behind that one, and a hydrogen down and to the left directly behind that one. So the way that we can do some measurements on this is by measuring what we call the dihedral angle, or the angle made through three bonds from this hydrogen right here down to the carbon, to then the back carbon, and right up to that back hydrogen. So on a circle, what you can see is that this dihedral angle right here, which we illustrate as a theta, is approximately 0 degrees because these guys are right on top of each other. So this would be, again, this is the eclipsed conformation, and it is very high energy and therefore very unstable. So let's rotate that around a little bit and turn it into something that is staggered. So as we spin this a little bit, it can move to the staggered conformation. And anything in between can, of course, exist. So you notice what I did is I took that front carbon and rotated it approximately 60 degrees. And what we end up with is something where the front is now located again right here in yellow. It's going to have a hydrogen up and to the right here. It's got one sticking straight down and then one up and to the left. Well, the back hasn't been rotated, so the back is exactly how it was in the first place. So it still has one straight up. And now what we can do is measure the dihedral angle between, again, the same two substituents. We want to keep using the same two substituents. And the angle that this is forming right here is 60 degrees. At 60 degrees, we have a perfectly spread out staggered conformation. The staggered conformation is stable, so it is relatively low energy and it is relatively stable. If we keep rotating, what you'll see is that we're going to just basically take this front. If we rotate the front and keep going, we're going to go back to another eclipsed conformation. So let's do that. So we're eclipsed again. So if we keep making that dihedral angle larger, this is again with just ethane, which is CH3CH3, we end up with, once again, going basically back to where we started. So with our Newman projection, we would have the H straight up, all right, and you can see that in this structure. We've got the H straight up, down and to the right, and down and to the left, and it's directly eclipsing what's right behind it. So I'm going to draw that again. But what we were comparing is we're always comparing that straight up hydrogen in the back, but what we've done is we've taken the hydrogen that was in the front straight up, so this one right here, we rotated it to the side so that it was in this position, and then we rotated it again so that the hydrogen that we started comparing, which will still be the one we're comparing, is right here. And the angle that we're now making is a dihedral angle of 120 degrees. So it's more spread out, except that we basically just turned ourselves right back into an eclipsed conformation. So once again, this is eclipsed, and once again, this is high energy, because in that eclipsed conformation, the hydrogens are relatively close to each other, and like charges repel, so once again, this is a relatively unstable situation. So finally, we can turn this thing another 60 degrees, which we will do right now. Alrighty. And that ends up rotating the front once again. So we took this front hydrogen right here and rotated it down. So we now have a much larger dihedral angle, but we've turned it right back to a staggered conformation. So looking right up here, we have this guy sticking pretty much straight down. So we'll draw that front carbon again, where we have the hydrogen straight down, one up and to the right, one up and to the left. And then in blue, we will draw our back carbon. And the back carbon is always illustrated by a circle instead of just bonds coming straight off of a dot. And once again, we will go back to our initial hydrogen in the back that we considered was the one that's still sticking straight up. But we've rotated the hydrogen that was in the front so that it's all the way down. So now our dihedral angle is 180 degrees. They're all the way apart from each other. And we've rotated right back to another staggered conformation. And this is once again relatively low energy because the hydrogens are spread out in three-dimensional space, so the electrons are spread out and it's much more stable. All right, so the way that we can draw kind of an energy diagram of this, if we consider energy from low to high, and we plot that against our dihedral angle, or our theta, when we started at 0 degrees, which you can see right down here, it was eclipsed. And eclipsed is relatively high energy. So we will plot that way up here in energy. When we move over to 60 degrees, which was our very first staggered conformation, at 60 degrees, it was a relatively low energy. And relatively because it is relative to where we started. When we rotated all the way to 120 degrees, we went right back to where we started at a high energy situation. In fact, that should be the exact same energy level as where we started. And then when we rotated again to 180 degrees, which we saw on the far right, that was back down to a staggered conformation, and the energy went right back down again. So you can see that going from kind of the local maximum, which is in terms of energy, a local maximum, a high energy situation is eclipsed. The low energy situation is staggered, and then back up to eclipse and down to the staggered once again. What we see is a sine wave in terms of the energy around these. So the actual plot of energy would look something like this, and it would just keep going up and down and up and down. It makes a sine wave. The reason for that is that 1 degree, 2 degrees, 3 degrees, right around here, is still relatively high energy, and whenever you're relatively close to 60 degrees, there's still relatively low energy. So there's a big change in between, but it's pretty good up here for a while, and then there's a steep change, and then it's pretty good down here for a while, and then a steep increase, and it's pretty good up here or pretty bad, pretty unstable up there for a while, and then back down again. All right, so hopefully this makes sense. But let's move on and see what happens when we don't have exactly the same substituents anymore. So let's consider the stability of any single bond within a larger molecule. So what I've drawn out right here is pentane. It's just 5 carbons in a row. And what I'd like to do is to consider the conformations along the carbon-2, carbon-3 bond. So carbon-2 would be this one right here. and carbon 3 would be this one right here. So essentially what we're going to do is look at this bond right here and how rotating it would make it more or less stable based on just however I've drawn it right now. So what we'll need to do is draw in our other bonds. So on carbon number 2, what we haven't drawn in, and we know is there, because it's a line angle structure, are 2 more hydrogens, and they should be in that conformation. And likewise, on carbon number 3, we'll have a hydrogen going up, coming out at us, and one going up and going away from us. So what we want to do is draw a Newman projection of where that is right now, and then start rotating it around. So let's imagine that our eyeballs are right here, and we're looking right at that front carbon in blue. So my front carbon in blue, at least the way that it's drawn, we'll put in our little dot right there. And from this point of view, if you imagine kind of an imaginary line right here, there's always going to be one of your 3 bonds, besides the one that's invisible, right? We're looking straight down this bond, so we can't see it anymore. We have one bond that is flat, and that's this one. It is right in the plane of the board, and it's going to be sticking straight up because it's above that plane of our eyeball right there. So we should have one sticking straight up, and then 2 coming down. One would be to the right and one would be to the left. So again, let's look at that. We have something coming straight up, but this something isn't a hydrogen. It's a CH3. So we'd have a CH3 straight up. We'd have a hydrogen down and to the right and a hydrogen down and to the left. All right, and the way that this is drawn, the carbon that would be in the back, which would be kind of the second carbon down our eyesight here. So this one would be our back carbon. That's carbon number 3. So we'll draw that in as a circle. All right, from our point of view, again, we're looking down this bond. So this is our front carbon, which we already drew. This is our back carbon. Our back carbon has one bond going this way. And again, from our field of vision right here, this whole thing is going to be down, because if we draw an imaginary line here, this is below that imaginary line. So we'd have a CH2, CH3 sticking straight down. We'd have 2 hydrogens at the top. So let's draw those in. We'd have a CH2, CH3 down. We'd have a hydrogen up and to the right, and a hydrogen up and to the left. All right, so that would be one conformation, and that's the only one that we've drawn here. But now that we have this turned into a Newman projection, what we can do is rotate. And so when we rotate, it doesn't matter which one you pick, and it doesn't matter which way you rotate. However, it's important to just be consistent. So what I'm going to do is I'm going to hold this CH3 consistent, and I'm going to rotate the ethyl group in the back. All right? So at this point, the biggest substituent in the front and the biggest substituent in the back are making a dihedral angle of 180 degrees. They're all the way apart from each other. It's important to consider the biggest things because the biggest things are going to be most prohibitive when it comes to stability. So let's take, we'll just take the back and we'll rotate it clockwise. So we'll send it that way. We're going to keep the blue part, which is the front, exactly the same. We're going to rotate what is in the back. So if we rotate what's in the back clockwise, our CH2, CH3 would end up being down and to the left. If we go about 60 degrees, we would have an H here and an H here. So now we've gotten to an eclipsed conformation. The angle in between our 2 biggest things is now about 120 degrees. 120 degrees. So let's rotate that guy again, and we will move it into that open space, and we'll rotate it into a staggered conformation. So once again, we will draw the thing that we did not rotate. The thing that we did not rotate was the front. So we're still keeping the front exactly how it is. But the back has now been rotated so that the CH2, CH3 is in this upper left position. And then we would have an H sticking straight down and an H up and to the right. And this time, the dihedral angle made between my 2 largest substituents would be relatively close. So we are at a theta, or a dihedral angle, of approximately 60 degrees. We have one more rotation to do. So once again, we will draw our front carbon exactly how it continues to be. We're going to take this CH2, CH3 in the back, and we'll keep rotating it in the same direction. So notice that we'll keep rotating clockwise. So now with our big circle, we'll have H's eclipsed, and now what we'll have, I know these are jammed in together, but we'll have a CH2, CH3 that's directly eclipsed with that methyl group coming off of the front. And these two things now have a dihedral angle of 0 degrees. So let's consider the stability here. Because these methyl groups have much more bulk, they matter a lot more than the H's. So the most stable of these conformations would be the one where the largest substituent in the front and the largest substituent in the back are as far apart as possible. And that's actually the way that we've drawn it up here. So this would be the most stable conformation. The least stable conformation would be the one where the biggest thing in the front and the biggest thing in the back are directly on top of each other. So this would be least stable. All right, so let's consider kind of those other guys in the middle there. Well, staggered is always better than eclipsed. So this would be kind of, I'll call this one stable with a little question mark, because it is stable, but it's not the most stable. And likewise, this eclipsed conformation right here, well, there's a CH3 eclipsing an H and an ethyl eclipsing an H, which is bad, but it's not as bad as a CH3 and an ethyl group directly eclipsing each other. So we will call this guy just kind of unstable. And again, I'll put a little question mark in there because it's not the complete least stable, but it's definitely unstable-ish. Well, we have names for all of these. We call this situation right here anti. Anti meaning across. This is the most stable. The biggest thing in the front and the biggest thing in the back are directly across. It's the most stable that we have. They're the farthest apart as possible. We call the one that's the least stable, where they are right on top of each other, as totally eclipsed. Oops, eclipsed. All right. And then we have two other words for these. We call this guy just normal eclipsed. And the one that is stable-ish, we use the French word gauche. And we can talk about in class what gauche means. But in terms of this class, what it means is it's stable, but it's awkward. It's not the best that it can be. So if we plot out the energy for this, what we'll see is that when you have 180 degrees, your energy is as low as possible. When we have our 0 degrees, way over on the right, it would be as high as possible. And what's going to happen is that the gauche is going to be low energy, but not as low as where we started. And the eclipsed is going to be high energy, but not as high as where we end up. So it'll still make a sine wave in between these guys, but it's not going to be a perfect sine wave that goes back and forth like it was before, because you can see that kind of this energy right here is very high. This energy down here is very low. And this one never quite gets that low, so it's a local minimum. This one never quite gets as high as the top, so it's a local maximum. So that's what happens when we rotate these guys around these conformations, is the way that it is given to us right here is actually most stable, but we'd have to draw that out to know it, and we'd have to look at that dihedral angle between the front and the back to see how far apart they are. Likewise, whenever you have the largest thing in the front and the largest thing in the back right on top of each other, that is always going to be the least stable conformation, which is going to be totally eclipsed. So the way that it will generally work out is like this, where you have alternating bonds going up, down, because in general that gives you the most stable conformation. So the way that we do line angle structures, where we just kind of do this, it's not just because it's most convenient, it's actually because these end up being, in general, the most stable conformations in three-dimensional space. All right, thank you very much for sticking with us. Again, I really encourage you to either get a set of models of your own or come down to my office. Outside of my actual office in room 211, I have a whole lot of these that you can play with. But it's worth doing. Some of you are going to see this easily in your heads, and some of you will probably take playing with it for a little while. I appreciate it very much, and I will see you in class.